Hello everyone. In this video we're going to talk about Columbic friction damping. So most of you have seen the viscous friction damping, right? So where we have this mass moving on a surface and there is a spring and there is a viscous damper, which we show like this. And the force of that damper is like Cx dot. Okay, and we have seen in a single DOF vibrating system like this, mass spring damper, that if there is no external force, the free response to some solution, to some initial condition like x0 not equal to 0 and x dot 0 equal to 0, right? So releasing it from rest from a non-zero initial condition, x of t is basically a negative exponential term like this times sine of omega dt plus some phi, right? And here it can be multiplied by some a as well, where this a and phi are coming from initial conditions, and omega d here is omega n times 1 minus zeta squared, and omega n is square root k over m, and this zeta is basically 2c over square root c over square root 2km. Okay, so and if this zeta here is between 0 and 1, which we call it underdamp, you have seen the response here, x of t versus t. So it starts from initial condition and then it goes like this. And here, the reduction in this amplitude, if you can draw these envelopes, these are exponential functions. Right? So the reduction in amplitude of oscillation is exponential when you have what? When you have viscous damping. This is what you have seen. Now the question is, if instead of this viscous damper, we have a Columbic friction. So the force is Ft equals mu k times n, where here n is the same as W, right? In that case, you know, also friction is gonna basically dissipate the mechanical energy of the system, the momentum here, that, or the potential energy to begin with, or you can start with momentum, or both of them, and over time converts it to heat, and the system amplitude starts to go down and shrink. The question is, what kind of response do you get? What kind of shrinking in amplitude do you get? Would you get exponential or something else? This is what we are going to talk about. By the way, again, the pictures and equations are all taken from Elements of Vibrations by Leonard Meyrovich. So here, the governing equation is mx double dot equals, here, if I write it, equals summation of the forces in the x. And here we assume that you release it from some non-zero x naught, which is bigger than 0, and from rest. So if this is the static equilibrium, you move it to the right, you bring it here to this x of 0 bigger than 0, and then release it. When you release it, because of the spring force, this guy is going to be moved this way. And the forces on it is this force here, which is k times x for arbitrary x, and of course the friction backward, which is when it's going to be Fd, and that Fd is simply mu k times W, where W and R are the same thing here. This N normal force is equal to W. So if you write the equation of motion here, it is clearly going to be negative kx plus mu k times W, right? This is your governing equation, and if you bring this kx to this side, so it becomes kx plus mx double dot equals mu k times W, and that is exactly this equation here. If you divide both sides of it by K. Because if you divide by K, what would you get? You get X plus M over K, right? X double dot, or divide by M, sorry. You have to divide by M, not by K. You have to divide by M, so this guy becomes 1, and this is going to be like that. And W over M, you know that's G, so that whole thing is going to be like mu K times G. So, or if you want, you can simply just write it as FD over M if you want, because that mu K times W, we just showed it with FD, so you can write it as FD over M. So your equation becomes X double dot plus K over M, which is omega N squared, times X equals FD over M. Okay, right? So far, let's write your equation. Now here, you do another extra thing to get equation number 2. What is that? So here, this side, you basically divide by a K and multiply by a K. So you multiply by a K and divide by a K, right? If you do that, what happens? This portion of it, which is FD over K, you rename it as small fd. So small fd in these equations is equal to capital Fd, the total kinetic friction, divided by what? Divided by K, the spring constant. And this M over K, you can write it as basically, so it's going to be small fd, let me write it, divided by M over K, right? You bring that K here to denominator, and this is omega, this is 1 over omega N squared. So it's going to be Fd over 1 over omega N squared, so it's just going to be Fd times omega N squared. Okay, so you finally get what? You get equation number 2. Let's do a little bit cleaning. So your governing equation is what? X double dot plus omega N squared times X equals omega N times Fd, where again here I add for you this Fd is the kinetic friction divided by K. Okay, and omega N is of course a square root K over M. Now, these are the initial conditions that we put the system subjected to. What is the solution to that? This is a second order differential equation. It's linear and it's not homogeneous. You have this as the exciting force. So the solution to this part is a cosine term, right? So that is going to be, because x0 is x0 and x dot 0 is 0, so it has to be a cosine. So that is going to be this term here. And this part here is going to give us a particular solution. And for particular solution, if that particular solution is constant x, so this guy is 0, you see that this omega n squared x particular is omega n squared Fd, so x particular is the same as Fd, and that is this guy here. So this is x homogeneous, this is x particular. And you might say, how come the amplitude is not x0, it's x0 minus Fd? Where does this come from? Well, it comes from the condition that your x at 0 should be x0. So if I plug in t of 0 here, that whole cosine becomes 1. So whatever this guy is, whatever this amplitude is, right, this one, whatever it is, plus Fd has to be equal to x naught. So clearly, if you take Fd to the other side, this amplitude has to be what? X naught minus Fd, okay? So this is your solution. Good? Now, this is the solution. And the solution is valid from t of 0, where you start, to some t equal t1 where this mass stops. Why does it stop? Because as it moves this way, your friction is always working against your momentum. Your spring force is all converted to momentum, and all that momentum is wasted into, or not all of it, a portion of it is wasted into heat by friction, and a portion of it is now stored in the spring. Okay, at that point, the momentum becomes zero. Why? Because x dot becomes zero. Now, what is x dot here? If I take a time derivative from this x, the x dot is clearly x0 minus ft times negative sine omega t. This ft is just constant. Remember, this guy was capital Ft over k is a constant force because that is mu k times w divided by k. Okay, that's a constant number. So in this case, x dot is 0 when the sine is 0. And the sine is 0 at t of 0, which is trivial solution. The next solution is when this whole thing becomes equal to pi. So t1 equals pi over omega n. Okay, so this solution here is only valid between 0 to pi over omega n. At that point, the system stops. And how much is x at that moment? So we plug this t1 back into x. This guy becomes cosine of omega n times pi over omega n. So this is pi. Cosine of pi is -1. So it's going to be -1 x0 minus ft plus ft, right? Which is 2ft minus x0, or we can write it like this. That's the same as saying 2ft minus what? x0. This is the position at which the block moves all the way to the left as much as it can, and then it stops. So at this point, x equals 2fd minus x0. Here, simply x equals what? x0. So it moves all the way to this position on the left. At this point, clearly, since this x is not equal to 0, you have some potential energy in the spring. And there is some spring force. Now, if the spring force here is enough to overcome the static friction, then the system is going to now move to the right. So if x of t1, this guy here, is big enough so that the spring force, k times x of t1, is bigger than the static friction Fs. This Fs is mu s times what? Times w. If this is bigger than that, now the spring force is going to push back. In this situation, if you draw the free body diagram, the spring force is pushing to the right. The friction, kinetic friction, is going to be to the left. So this is your Fd, this is your k times x. So in this case, if you write equations, it's going to be mx double dot equals positive kx minus ft. Right? And you might say, oh, what comes here? Is the spring helping the vibrations? No. In this case, remember your x is to the left side of the equilibrium. So this x is negative really. Okay, you are now to the left side of the equilibrium. This x here is negative. This other amplitude. So now your x is negative, so this can be considered, if you go with a positive x, this can be considered like negative kx, where now this x is positive. So if you bring it to this side, your equation becomes mx double dot plus kx equals negative ft. And compare this against what we had last time. It was this. Or if I bring the kx to this side, it was this. Remember last time the friction was what? The friction was this way. So last time mx double dot plus kx was positive ft. This time is what? Negative ft. And if you want to combine these two equations, this one and this one, if you want to combine them, the best way to combine it is what? here, looking at, if you bring this guy here, it becomes mx double dot plus kx and then plus minus ft equals 0. Now, which case is plus, which case is minus? When this block was moving to the left, x dot was negative, right? But here, this term was positive. Here, this block is moving to the right, so x dot is positive, but this term was what? Negative. So whatever is on this side is ft times what? Negative sine of x dot, right? The negative sine of x dot on the left-hand side should be multiplied by ft. Now, if you bring it to the left side, that negative sign becomes positive sign. So instead of writing it this way, you write it as positive sine of what? X dot times ft. And that is exactly this equation 1 here. So if you wondered where equation 1 comes from, that is for the fact that wherever the object moves in which direction, the friction is opposite to that. So that's why here on the right hand side it is negative ft sine x dot. If you bring it to this side, it becomes positive ft sine x dot. Okay, so now how far does it go as it moves to the right? How far does it go? Last time we seen how far it goes to the left to stop. Now how far does it go to the right to stop, knowing that this time the governing equation is this? Remember? Right? We had this negative ft here. So the equation, the governing equation, is just like last time. It's just like last time, except the sign of this friction term becomes negative instead of positive. Again, the solution to that is going to be something like this, because now you have two new initial conditions. X dot at time t1 is 0. Remember, you stop at the very left, but x at time t1 is not 0 anymore. It is what? It is this here. It is that 2ft minus x0. So this is the new initial displacement, and that is the new initial velocity, and this is your governing ODE. If you solve this subjected to those two initial conditions, the solution becomes this. Again, it has a homogeneous solution, this part, and it has a particular solution, which is this part. Now, why is this amplitude this time x0 minus 3ft? Because again, whatever this a is, if you plug in t2, and t2 is the time that it, t1, sorry, if you plug in t1, x dot at t1 should be equal to what? To 0. Okay, which it is, and x at time t1 should be this. So when you plug in t1, as you remember, omega n t1 becomes pi, so that whole cosine becomes -1. So -1 times a minus fd should be 2fd, right? Should be equal to 2fd minus x0. So if you take this to the other side, it becomes 3ft. If you negate it, it becomes x0 minus 3ft, and that is exactly this one that you can see. Okay, here I did some cleanup. So this is your solution this time, and remember last time your solution was this guy in the green box. Now, last time your solution was only valid between what and what? Between 0 to t1, and t1 is when it stops on the very left end. So now as it starts moving on the right side, how far does it go before, again, it stops somewhere here? What is the x at this point, and what is the time at this point where x dot becomes 0 again and you stop? Well, for that, you need to take a time derivative again. So if you take a time derivative from this ft is constant, so you get this, because derivative of cosine is negative sine, And again, this x dot is 0 when this sign equals 0. This whole thing should be 0. And this is 0 when this guy is an integer multiple of pi. Now at t1, it was equal to 1 pi. So now since the stop time for on the right side is bigger than t1, so this guy should be equal to 2 times pi. So this t2 should be 2 pi over omega n. That is what you have. Okay, at t2 equal 2 pi over omega n, x dot is going to be equal to 0. So now you plug in t equal t2 here. So this whole thing becomes 2 pi, and cosine of 2 pi is simply equal to 1. So x at t2 is going to be x0 minus 3 ft minus ft. So it's going to be x0 minus 4 ft. Okay, so the time you stop here is t2, and the amplitude is what? As we just saw, it is x0, right? Minus what? Minus 4 times ft. Right? Let me clean up this portion here so we can see a little bit better. Okay. So now if I go back, what do I observe? First, I started at x0. This was my initial amplitude. After half a cycle that I moved to the left, my amplitude was 2ft minus x0. You see, instead of being negative x0, it's now basically negative x0 minus 2f. The reason it is written this way, so you see that instead of being negative x0, is negative x0 minus something. So your amplitude in half cycle was reduced by 2ft. And when you come down to full cycle, now your amplitude, instead of x0, now you're back to what? You're back to x0 minus 4ft. You see, so after another half cycle, you go to full cycle, now it is reduced by 4ft. And this can be repeated. So each half cycle you go, it drops by what? When you go from here to here, it drops by 2 FTs. And when you go back to the full cycle, it is dropped by 4 FT. If you go 2 cycles, now it is going to be dropped by what? It's going to be dropped by 8 FT, and so on and so forth. So 4 FT per cycle is the amount of reduction in amplitude, and clearly if you draw these envelopes, you see that the amplitude decrement is linear. The decay is linear. It's not like what? Like viscous, where these drops were what? They were exponential. Okay? So the Columbic friction has a damping effect, but it reduces the amplitude by a linear amount per cycle as opposed to exponential one. And this is what I wanted to demonstrate for you and the solution to this case. So hopefully the video was useful to you. I'll see you in the next lecture. Thank you.